All right, well, let's get started on the daily 2 number 46, okay? Just gotta check one thing in attendance here, okay. So daily 2 number 46, I'm going to share the screen and let's go through daily 2 number 46, which I wanna say is right here. Yeah, all right, so the wavelength of a certain wave is 2 meters and the frequency is 400 hertz. What is the speed of this wave? Well, V equals F lambda. V equals F lambda. The frequency is 400 hertz and the wavelength is 2 meters. And that leads us to an answer of 800 meters per second. 800 meters per second, yeah. And I saw that, looking at the responses, I saw this in many cases. Not all, but many cases. So that's good. Let's see. Well, about 2/3 got that correct. A little more than 2/3. So the most popular incorrect answer was 200, and that's by dividing. But the equation is speed is equal to frequency times wavelength. All right. All right. And then the second question: a box of 10 kilograms is being pulled across the floor at constant velocity by applied force of 40 newtons. What is the force of friction? Keywords here being at constant velocity. At constant velocity. Because then at constant velocity, we know that the applied force and the friction force are the same. Okay? So the correct answer is 40 newtons. Okay? 40 newtons. And looking at the responses, about 70% got that correct. The rest were not. So yeah, the keywords there being at constant velocity. So we're at 70% success, which is good, but I'd like better. Okay, so questions about daily 2 number 46? No? All right, let's go back to Wednesday's, daily 2 number 45. Which of the following affects the speed of a wave? And the correct answer is the medium it is traveling in. Okay, the medium it is traveling in. The characteristics of the wave itself plays no part. So the amplitude, the frequency, it's not about the wave. It's about what it's traveling in. Okay, and so the correct answer is the medium it is traveling in. And a little over 80% got that correct, which is good, but I hope by test time it's 100%, because I'm going to ask you that question. This question will be on the test, okay? Just saying. And I very much hope you answer the medium that it is traveling in, okay? And then the second one, approximately how tall am I in centimeters? And so I'm gonna stop sharing. Let's measure me, all right? And so I'm gonna do that by over here. Now, meter stick is 100 meters, right? 100 meters. So I'm taller than 100 meters, right? How much taller? Come on, 100 meter stick here. Well, I'm here. Not quite. Right here. Right about here. Which is about 78, almost 80. So my height is 180 centimeters. Okay. If you buy skis, I think you skiers out there, don't they sell skis in centimeters? Like, you buy 192s or something like that, and that refers to the length, 192 centimeters. A skier told me that once. Okay. Is that true? Any skiers out there? No response. Yeah, I think from what a skier told me once that they sell skis by length and the length is in centimeters. Okay, so that was my height, and then that was true the majority of the cases, majority of the responses, 84%. There were a few that says I was 1,800 centimeters. No, that's that has I'd be a giraffe then. Not even. That's super tall. So anyway, 180 centimeters is correct. Okay. Questions, comments on those? All right. Then we're going to head into the next part of this unit. And so I'm going to get back. I'm going to share the screen again. Share screen again. Oops. And I'm going to get back into my PowerPoint. Okay. Now, the last thing we talked about was the audible range of humans. Talked about this, and the audible range of humans was 20 to 20,000 hertz, and lower than 20,000 was infrasonic, and greater than 20,000, less than 20 is called infrasonic, greater than 20,000 is called ultrasonic. Okay. And we talked a little bit about that. All right, next. Next, I want to talk about sound intensity. Okay, now when the sound wave travels through the air, it's a pressure wave that impinges upon our eardrum and it makes our eardrum vibrate. Okay, and that's how we absorb the sound energy from the air. It's the vibration of our eardrums. Okay, now if our eardrum doesn't vibrate, then then we don't receive the sound. Right now, remember the energy of a sound depends on its amplitude. Remember, the energy of a mechanical wave, the energy of a sound wave depends on its amplitude. Okay. Now, I'm going to introduce an intensity scale. I'm honestly not going to test you on it. So you really don't have to write this stuff down if you don't want to, but pay attention anyway. Okay. The energy of a sound wave depends on its amplitude, and the scale that we use is a very strange scale because we base it on the human body, which we never do, right? The length foot was based on the human body, but that went out a long time ago, right? Well, a couple hundred years ago in the metric system. We don't do that anymore. But this is the one scale that I know of that's based on our bodies. Now, the softest sound that can be detected by the human ear has an intensity of 1 times 10 to the negative 12 watts per square meter. That's an incredibly low power wave, low intensity wave. Okay, and our eardrums must be incredibly sensitive to absorb an energy like this. Okay, and so this is why, and this is called, by the way, the threshold of hearing. Okay, the threshold of hearing. It's the faintest sound that we can possibly hear in the human body. Okay, now I'll stop sharing for a minute. Our eardrums are incredibly sensitive things. That's why you should never, ever put anything solid into your ear. You should never touch your eardrum with anything solid because it is such a sensitive membrane that it's very, very easily damaged. So if you want to clean out your ears, don't even stick like a Q-tip in there. That's not good. That's not even good. Do it with liquid. A doctor does it with liquid only. Or they're extremely careful. That's why they're doctors. Never stick anything solid in your ear because it's very, very easily, your eardrum is very easily damaged. When you dive down in the bottom when you go down diving into water, where's the first place you feel the pressure? Your ears. Okay. Does that mean that the water's not pushing on every other part of your body, including your eyeballs? Yeah, it is. But you only feel it in your ears because it is so very, very sensitive. So never stick anything in your ears, okay? Okay. Now, maybe you have been, now let's ramp up the amplitude of the sound. Have you ever been in an environment that was so loud that your ears actually hurt? Where the sound was so loud, your eardrums actually hurt? Has anybody ever been that? That's because your eardrums are vibrating so violently. It's saying, hey, stop it. I'm hurting. Body, get out of there. Right? Well, this is called the threshold of pain. And it has an intensity of 1 watt per square meter. This is called the threshold of pain. Okay? Only 1 watt per square meter can cause your eardrum to vibrate enough that it hurts. Okay? Okay, well, this leads us to an intensity scale, okay? This leads us to an intensity scale. The threshold of hearing is 1 times 10 to the negative 12 watts per square meter, and the threshold of pain is 1 watt per square meter. That's 12 factors of 10, okay? So if we wanted to measure sound and put it like on a meter, and a dial on a meter, would our scale be that to 1? or 1 to that? No, that's ridiculous because it's too large of a scale. It's too large of a range. So we need to knock this thing down a little bit, right? So instead, let's use powers of 10. 1 is 10 to the 0. A trillion is 10 to the 12th, right? So instead of using this, let's use 0 to 10. And that's what they did, okay? They defined this unit, 0 to 10, 0 to 12, sorry, 0 to 12, based on powers of 10. And they called each one of these, they called it a bell, after Alexander Graham Bell, okay? But they said, you know, we went too far. We went from a range that was too big to a range that was too small. We want to have a little more definition in our scale. So what they did was they cut each of these into tenths. They took each bell and they cut it into 10 equal pieces. And so it changed from 0 to 12 to 0 to 120. So each is a tenth of a bell. And what is a tenth of a bell called? Well, a tenth of a meter is called a decimeter. A tenth of a bell is called a decibel. And that's where the decibel scale comes from, okay? I'll never test you on this, by the way, okay? But that's where it comes from, okay? Now, the threshold of hearing is defined as 0 decibels, and the threshold of pain is 120 decibels, okay? All right, now, in case you're interested, here is the formula, the equation for the decibel scale. And here is a table of typical sounds and their decibel level, okay? All right, the threshold of pain, okay, is 120, all right? Actually, in this scale, they have it a little bit higher, but normally, as I learned, it's 120. And this is a logarithmic scale, which is a little bit different, a little bit weird. Another logarithmic scale because it's based on powers of 10. Another logarithmic scale that you may have heard of was a Richter scale, what they used to measure earthquakes with. They use a more sensitive one now called the magnitude moment scale, but people don't hear that as much as that you may have heard of the Richter scale. Okay, so that's another logarithmic scale. Okay, now I'm not going to test you on any of that stuff, but I just wanted to introduce you to it. If you're interested, then get into this slideshow and I get into a little more stuff, you know? I'm not going to take the time to do this, but I get into a little more stuff, okay? All right. But I'm just going to kind of blow past that. And I want to talk about the ear. Okay, this is the structure. This is a diagram of our ears, okay? Our ears are incredibly sensitive devices. How do they actually absorb the sound energy and transmit it to our brains where we can interpret it? How does that happen? Well, here's how it happens. This fleshy part of the ear, you know, this thing that's hanging on the side of your head, is kind of used like a funnel to funnel the energy into the channel, okay? And so it goes down the channel, all right? And it lands on the tympanic membrane, which is a fancy name for the eardrum. And it causes the eardrum to vibrate, okay? Now, these vibrations are really, really small, okay? It doesn't vibrate much at all, but it vibrates a little, okay? And what we need to do is to amplify that a little bit. So these three things are bones. They're called the malleus, the incus, and the stapes, or more colloquially, the hammer, the anvil, and the stirrup. These are the three. How many bones do you have in your body? How many bones in the human body, biology students? It's not 270. I thought it was like 208. I thought it was 208. I think 206, 208. I think it's 208. And of the 208 bones you have in your body, the three smallest ones are in your ears. Actually, the six smallest ones, I suppose. Here's the hammer, the anvil, and the stirrup are the three smallest bones in your body. And what they do is they act as levers to multiply the vibrations. They amplify the signal, okay? And then they send the signal to this coily thing, which is called the cochlea, okay? The cochlea. And 206. Okay. Depends on what age you are, really? Okay, let's just consider when you're full grown. All right, when you're full grown. Um, it sends it to this spirally thing, which is called a cochlea. Now, a cochlea is a tube. Okay, it's a coiled up tube, and on the inside of the tube are little hairs called cilia, Cilia. Perhaps you remember those. Maybe they referred to them in biology class. And the vibrations of the liquid inside the cochlea, okay, is the bones vibrate, send the vibrations to the liquid, and the liquid vibrates the hairs. And it's those hairs that transform the signal into an electrical signal, which is sent to the auditory nerve and to your brain, and that's how we interpret sound. It's an incredibly delicate mechanism and easily damaged. Okay, so take care of your ears. Okay. Now, if you've ever gone up in an airplane, all right, you felt the pressure in your ears first. You need to equalize the pressure because when you go up in an airplane, the pressure goes down. The air can get in through this eustachian tube, okay, which is connected to your mouth somehow. All right, so you can yawn or chew. Some people yawn, some people chew gum. What works for me is taking sips of water. So when I'm going up in an airplane, when I'm flying, I always take a bottle of water along. And when I feel pressure in my ears, I take a sip of water. And the swallowing serves to equalize the pressure. Okay. Other people chew gum, other people yawn, stuff like that, just to equalize the pressure in your ears. I have a harder time coming down than I have going up in an airplane. Okay. All right. Anyway, so that's how the sound is transmitted to your brain. One other thing that's here, our balance. You know, they say we have five senses, right? Sight, sound, taste, hearing, and smell. Well, psychologists have now kind of expanded it, and so they say we have 8 senses. Okay, one of them is the sensation of heat with our skin. Another one is balance, and I can't remember what the 8th one is. And our sense of balance is actually governed by our ears. Okay. All right. Now, I'm going to stop sharing for a minute. If home experiment, take an egg, a raw egg. Okay. Take a raw egg, spin it on the counter, and then touch it and then let it go right away. And when you spin it, okay, the egg is spinning, egg is spinning, egg is spinning. When you stop it and let it go again, it'll start to spin again. Why? Oh dear. Sorry. My bad. Start it, spin it, so it's going whoa, 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 whoa. Touch it and then let it go again. And it'll resume spinning. Why is that? It's because the inertia of the liquid inside. Okay, you stop the shell, but the liquid is still moving inside, and it will cause the egg to start to move again. Okay, a raw egg. Now, if you hard boil the egg, then it won't because it's solid. But a raw egg, spin it, touch it, and let it go right away. Stop it and let it go right away, and it'll begin to spin again. Okay. All right. Now, when you, I got to share again. Got to get into the share thing again. When you get here, resume. Okay. Your sense of balance is governed by the liquid in your cochlea. Okay. And this is when you get dizzy. If you spin in a chair, when you spin in a chair, the liquid in your cochlea starts to move. When you stop, the liquid in the cochlea is still moving. And it's just like the liquid in the egg. And it will cause you to become disoriented. It'll cause you to become dizzy. And you'll stay dizzy until the liquid in the cochlea settles down. And how long does that take? How long does it take you to stop being dizzy? Spin around on a chair, and stop. You'll be dizzy for what, 20 seconds maybe? It takes that long for the liquid in the cochlea to settle down. Okay. So the reason you get dizzy, your whole balance mechanism is in your ears. And that's how you know which way is up. Okay. All right. So your ears are responsible for more than just hearing. It's responsible for your balance as well. Okay. All right. All right. Now, let's see here. What do I want to do now? Oh, next. And this is really the main topic of the day. Speed of sound. How fast is sound transmitted through media? Okay. Now, sound is transmitted from place to place by collisions between particles. The tines of this tuning fork compress the air molecules, and so it pushes one air molecule into its neighbor, which pushes its which pushes it to its neighbor, which pushes it to its neighbor, and on down the line. So sound is transmitted via collisions between particles. Okay, and because of this, they say sound is a mechanical wave. A mechanical wave is a wave that needs a medium to travel through. Okay? Mechanical waves need a medium to travel through. Now, the counterpart, well, actually, now let me say that. Let me not say that. Now, so sound is a mechanical wave, one that needs a medium to travel through. All right, I'm gonna stop sharing for a minute here. So now let's talk about outer space. If you see these, if you watch these space movies, Star Wars and things like that, and they're going through space and they're having this space battle. So you shoot this laser into the other ship, and the other ship goes and it just blows all these sounds of explosions, blah 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 blah. That would never happen because the sound of an exploding ship 1,000 kilometers away sound can't travel through a vacuum. Okay, let me ask you. I'm going to say this. Sound can't travel through a vacuum. Why not? Chat window time, or better yet, unmute and say. Sound can't travel through a vacuum. Why not?
There's no particles for the wave to collide with?
Yes, exactly. There are no particles to collide with, right? So sound can't travel through a vacuum, right? So, all these from space movies, that's just for effect, Hardly any do it right. Hardly any have an explosion out there that you can see, but you can't hear. The old Star Treks did, okay? Very few space movies do, okay? And if they do, I applaud them, right? Because, but no, they're just, okay, here's my joke about that. If you hear the sound of a ship exploding, that's really bad. Guess why? Guess why? If you hear the sound of a ship exploding, that's really bad. Why? Yeah, I know, they want the loud boom, yeah. But if you hear the sound of a ship exploding, that's bad. You know why? Because you're on it. Because you're on that ship, yeah. Yeah. So, yeah, I know they do it because people don't know science. They need to know their physics. Now, sound can't travel through a vacuum. But okay, well, how do they talk in space? How did Buzz Aldrin talk to Neil Armstrong on the lunar surface? Well, they didn't use sound waves, at least not between their location, between Buzz and Neil. They used radio waves because radio waves do not need a medium to travel through. Radio waves are electromagnetic waves, which are light, all forms of light. And we'll talk about this later. All forms of light, and there's 7 kinds of light. Okay, radio waves is one of the 7, and those are electromagnetic waves. Electromagnetic waves can travel through a vacuum. Mechanical waves cannot, and sound is a mechanical wave. Okay, all right. So, sound cannot travel through a vacuum since there are no particles to vibrate. Now, the speed of sound depends on how fast the particles get to their neighbors. Okay, it is a finite speed. It takes a certain amount of time, not a lot of time, but it takes a certain amount of time for one air molecule to get to its neighbor. Okay, and it's actually temperature dependent, because if you remember your chemistry, hot gases, hot molecules vibrate faster than cold molecules. Okay, hot gases, stop sharing for a minute. This is a cold gas. This is a hot gas. Okay, the energy of heat is contained in the kinetic energy of the particles. Slow, fast, and cold, hot. And the hot ones can get to their neighbors more quickly than the cold ones do. So the speed of sound is temperature dependent. Okay. Okay. Now there is an equation for this, but I don't know what it is. I'd have to look it up. All I know is this: at 0 degrees Celsius, sound travels through the air at 331.5 meters per second. You can measure this. Okay. You can measure this, 331.5 meters per second. I'd like you to write that down. Put it in your equation bank. And it's temperature dependent, okay? As it turns out, for every 1 degree Celsius rise in temperature, the speed increases by 0.6 meters per second. This had to be measured, okay? For every 1 degree Celsius lowering of temperature, it goes slower by that same amount. It's linear, at least over the range that we live in. Okay, and so that actually leads us to an equation. The speed of sound is equal to 331.5 meters per second plus 0.6 times the temperature, where the temperature is measured in Celsius. Write that down. Put it in your equation bank. We are going to use it a number of times through the rest of this unit. Okay. It's also, oh, by the way, it's also pressure dependent. This 331.5 meters per second is at STP, standard temperature and pressure. There is a pressure dependence also, but it doesn't, since the pressure doesn't vary nearly as much as the temperature does, we kind of ignore, at least in Physics 1 classes, we ignore the pressure dependence. Okay. All right. Now, room temperature, the room that you're in, the room that I'm in, the range that we're comfortable with is about 20 degrees Celsius. Perhaps a little bit warmer, but we'll call it 20 degrees Celsius, just to get a nice round number. What is the speed of sound at this temperature? Okay, you have 4 choices. Now, to solve this, take this 20 degrees Celsius and insert it for T. Okay. All right. Insert it for T. And we're going to be doing this a number of times throughout this unit, especially when we talk about musical instruments. Okay, music produced by instruments. And we'll talk about that next week. Okay. All right. Okay, what do you got? Fingers, chat window. Choice number 1, choice number 2, choice number 3, choice number 4. What do you think? What do you think? 2 is a very popular choice. 2 is a very popular choice. No. 343.5 meters per second, which, yes, that was choice 2. Okay. This was choice 2. All right. So we will become very familiar with doing this. Okay. Whatever temperature your room is, or outside or wherever, put it in there and you can get the speed of sound. Okay. All right. Now, the speed of sound actually has a special name. Curious. Does anybody know what they call the speed of sound? I bet you've heard of it, but I don't know if you can come up with it. Not supersonic, but we'll get to that. No. So the speed of sound is actually called Mach 1. Mach 1. Okay, and Mach that comes from a a Austrian scientist by the name of Ernst Mach. Okay, and Avery, you have a question? Unmute and ask.
Oh no, I was just that was an accident. Sorry about that.
Okay, that's fine. Mach comes from Ernst Mach, who was an Austrian physicist, and to my knowledge, he had nothing to do with sound. Okay, so I'm not sure why they called it. Maybe just because it sounds cool. I don't know. No idea. But they call the speed of sound Mach 1. And it's 343. Well, it depends on how high off the ground you are, but it converts to around 750 miles an hour. Okay, 750 miles an hour. Okay, which I'll never test you on that 750 miles an hour thing. In fact, I'll never test you on any of this stuff coming up, but it's just kind of interesting. All right, now, back in when they invented airplanes, 100 years ago, they were driven by propellers, right? And they developed better propellers and all that, but they could never ever approach, going how fast sound was. All right. Now, but then in the 40s and the 50s, the Germans, I think it was the 50s, the Germans developed jet engines. Okay. And jet engines allowed planes to go much, much, much faster. Okay, so they could see it coming. So planes are going, 400 miles an hour, 500 miles an hour, 600 miles an hour. And the question was, can planes go faster than the speed of sound? Can they break the sound barrier, right? The sound barrier, right? And here's the science about that. If you're traveling through the air in front of you has to get out of the way, right? Otherwise, you're going to walk into a wall, right? So the air particles have to get out of the way. Well, air molecules are moving pretty fast, and they can certainly get out of the way of me walking across my room. And they're moving quickly enough to get out of the way of propeller-driven planes, the nose of the plane pushing on the air in front. The air molecules have to have enough time to get out of the way, because if they don't, they're just going to push up into each other and you're going to get a wall. Okay? Hence the name sound barrier. And it was thought that if the air molecules can't get out of the way, the wall of air is going to be so hard to push through that it's going to overcome the integrity of the plane, and the plane's going to fall apart. Right? So there was a real question as to whether a plane could survive going the speed of sound, right? Well, eventually they did, of course, okay? And the first guy to break the sound barrier, and I use that term loosely, is a guy by the name of Chuck Yeager, who was a Navy test pilot. And he did it in 1957 in a plane that he called Glamorous Glennis. He named it after his wife, okay? And you can see this plane. It is hanging in the Smithsonian Museum in Washington, D.C. And I really, really suggest checking out that museum. There's actually two Smithsonians. One's on Capitol Mall, and the other one's out in the airport. Go to the one out at the airport. Well, go to both. But this plane is hanging in the one out by the airport because it's a lot larger building. Okay. So anyway, so he was able to break the sound barrier. And after that, planes can routinely break the sound barrier. Okay. Here's a picture of a plane that's achieving Mach 1 or breaking the sound barrier. All right. And I have this. Now, when a plane does this, it is pushing all the air molecules in front of it together. Okay. Or it's pushing the air molecules together. All right. I'm not exactly sure. I've never studied supersonic physics, and supersonic is speeds above Mach 1. Okay, I've never studied, so I don't know why it forms at the tail, why it forms around the cockpit. I don't know because I've never studied it. But check this out. I'm gonna replay that. I'm gonna replay that because I paused. Do you hear that? It sounds like thunder, right? If you've ever heard a shock wave, okay, or a sonic boom, that's what they call it, a sonic boom. It sounds like thunder.
Watch the vapor build up on this airplane. Look at that. Oh, yeah!
One more. Sounds like thunder, okay? And they call that a sonic boom, right? Now you might wonder, well, why does it sound like thunder? Well, because it's the same thing as thunder. Okay, I'm gonna stop sharing for a minute. Thunder. Thunder is produced by lightning, right? Now a lightning bolt is well, actually, let me talk about the sonic boom. When a plane is going at Mach 1, it is pushing all the air molecules together, right? And that white thing that you saw around the plane, that white thing stuff isn't smoke, it's water vapor. It's the same thing as a cloud, because it's not only pushing the air together, it's pushing the water vapor together. So you get a little cloud around the front of the plane that will eventually, they'll separate and dissipate. Okay, and so you get air, but that's the visible part. The air molecules are all pushed together in what's called a shock wave. Okay, and this is what happens. And it sounds like thunder because it's the same thing. Now, real quick thing about lightning. Okay, lightning is electricity that goes from the ground to the cloud and back and forth, and it's a bolt of electricity about as thick as your arm, and it's hotter than the surface of the sun. So when a lightning bolt comes down, let's say this is a lightning bolt, okay? It's hotter than the sun, and so it superheats the air around it. The air right next to the lightning bolt gets superheated, and hot gases want to expand. So the gas right next to the thunder, right next to the bolt of lightning, expand very, very quickly, and it creates a shock wave. A wave of super compressed air, and this emanates out through the air. A very, 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 very tight compression that, just like any other longitudinal wave, will emanate out through the air. And when it gets to our ears, it sounds like thunder. Well, the shock wave around a plane going Mach 1 is the same thing. Okay, it's just produced by different means. All right, it's produced by a plane going super fast instead of superheat. All right. So this condensation shock wave will, and I have another thing here. These are the shock waves around a plane, okay, produced in the laboratory. And when they go outward, it sounds like thunder. Okay. All right. So yeah, and if you just YouTube, not right now, but if you YouTube planes, going Mach 1, then you'll be able to find this stuff. You'll be able to find the stuff without too much trouble. All right. Okay. Let's see. So Mach 1 is about 750 miles an hour. All right. Then what's Mach 2? What's Mach 2? Well, yeah, right. And I see that. Okay. What is Mach 2? Well, Mach 2 is twice the speed of sound, which is about 1,500 miles an hour. Okay. What is Mach 3? Well, Mach 3 is 3 times the speed of sound, or about over 2,000 miles an hour. Okay. Okay. I know what you're thinking. You're wondering, has there ever been a plane that can go? Oh, by the way, now after jet engines, military planes routinely break the sound barrier. Oh, actually, I got to go previous to this. Before I talk about Mach 2 and Mach 3, notice that video that video is over water. Okay, that video, let me advance it a little bit. This video is over water, okay? Because it's, because these shock waves, okay, I got a question for you. Now, usually don't get rip-roaring thunderstorms around here, but maybe. Has anybody ever been, has lightning ever struck so close to your house that it rattled the windows? Has that ever happened to you? Yes? It happened to me when I was living in Wisconsin. Okay. Yes? Okay. Yeah. Well, why is that? Well, it's because the shock wave, the compression that's emanating out from a lightning bolt, that compression wave is vibrating the air molecules. Okay. And if it hits something like a window, it could vibrate the window. Actually, if it's close enough, theoretically, it could shatter the window from the vibrations. Okay. All right. This is why it is illegal to go supersonic, to break the sound barrier, to go supersonic over land. Okay. Because they don't want, well, they still do it in isolated places, but certainly not over a city, because it could damage things. For example, well, I'll get to that in a minute. I'll get to that in a little while. So they go supersonic primarily over water. But if you've been to an air show, or at least over a big stretch of ground where there's nothing in between, there's no glass to shatter. If you've been to an air show, maybe a military jet will go supersonic just because. All right. Okay, let me get back to this. Any questions? You can stop me at any time if you have a question or a comment or an observation. Yeah. Anybody know of a good air show around here? I just moved here, a little more than a year ago. I don't know. I mean, because I like to see those. Right. I suppose I could look it up. I can take that out. All right. Anyway, what am I trying to do here? Get back to my Reno has. Yeah. Hello. Oh, okay. Okay. I'll check it out. It's worth going to Reno. That's not too far. So I'll check that out. All right. Anyway, Mach 2 is twice the speed of sound. Mach 3 is 3 times the speed of sound. Now, military jets routinely go over Mach 1. Can they go over Mach 2? Can they go over Mach 3? Has there ever been a plane that has gone faster than Mach 3? And the answer is yes. Okay. Here's a picture of the SR-71 Blackbird. Okay. It was a Navy plane that flew back in the 1970s. Okay. Now, I know what you're thinking. Why did it have to go that fast? Well, this SR-71 Blackbird is a spy plane. And they used it, where's my cursor? They used it to spy on the Soviet Union. And it went so fast that the missiles normally a missile couldn't catch up to it to shoot it down because it flew so fast. There was one guy that actually got shot down. Okay, but that only happened once. This is before the days of spy satellites. Okay, they flew planes over to take pictures. Right, SR-71 Blackbird. You can see one of these hanging in the Smithsonian Museum in Washington, D.C. I highly recommend going and check it out. Now, they don't fly these anymore because they're extremely expensive. Okay, it was basically a flying gas tank. And so it was extremely expensive to build, extremely expensive to fly. So when they started putting satellites up in space that could do the same job, then they retired these things. So they don't fly. These don't fly anymore. Okay. Okay, that was a military jet. Has there ever been a passenger jet that went supersonic? Has there ever been a plane that you or I could fly on that went supersonic? And the answer to that is yes. Okay. Here's the supersonic passenger plane. Perhaps you've heard of it. It was the Concorde. Okay. The Concorde. And it was made by the French. Okay. And it cruised at Mach 2. It took off from Paris or London, and it flew to New York and Washington, D.C. It flew across the Atlantic. And so you could get on the Concorde in the morning, fly over to London or Paris, have lunch, and fly back and get back in time. You could be back in your home in time for dinner. Okay, it was that fast, right? Of course, it was ungodly expensive. When I say you or I could fly in it, well, we could if I had a way different job. If I had a much different job than I have, because the ticket for one of these things probably costs more than I make in a year. You know, so no, I could not afford to. Do planes flying that fast have any effects on passengers? No, they don't. It's just like the plane that you can take off at Sac Airport. All right. The acceleration is probably a lot more and probably a lot longer, but no. As a matter of fact, if it's smooth riding, it's the same thing as if you're sitting in your room right now. You would never know the difference. Okay. Newton's first law. All right. Now, do these fly anymore? And the answer to that is no. It first flew in 1969. But they had problems with these things, okay? Because if you know, again, it was a flying gas tank, because to go that fast, it requires tremendous amounts of fuel, okay? But they had a couple of accidents with this thing, and to the point where they decided to retire this. It wasn't worth it. And the last one occurred in 2003, after a crash that killed all 109 passengers. Okay. Here's what happened. It was taking off from an airport outside of Paris. Okay. And now, before I say that, where do planes carry their fuel? Does anybody know? Where do planes carry their fuel? Where is a lot of room for planes to carry their fuel? Anybody want to guess? The wings. Yeah. The wings in the belly. Yeah. Yeah. They fill up the wings with gas. And if they have room in the underside, there's a center fuel tank also at the bottom that they can fill up also. But they fill up the wings. So this Concorde was going down the runway in an airport outside of Paris, and it ran over a piece of metal that they figured this out later. It ran over a piece of metal that had fallen off a plane that had just taken off previously. That piece of metal shredded the tire, and the pieces of tire cut the underside of the wing. They cut it open, and so fuel started spilling out. Somehow or other, it ignited. So the fuel that was coming out of the bottom of the wing was on fire. Now, the pilot did not have time. He didn't have enough runway to stop. So he took off and tried to circle around and tried to make it back to the runway and land. But they didn't make it. It crashed. And I believe it crashed, memory serves that it crashed into a hotel and killed some people there too. I may be wrong about that, but it crashed and killed all 109 passengers. Okay, that was not the first time that happened. So they said enough is enough. And oh, by the way, the 109 passengers tended to be kind of important people, CEOs and entertainers, and people who could afford to buy that ticket. They weren't just slobs like me. So that wasn't the first time that happened. So they said enough is enough. We're going to retire this thing. So they don't fly them anymore. Okay. And that was the last time a passenger plane has gone supersonic. All right. You can see a model. You can see one of these planes in the Smithsonian Museum in Washington, D.C., out by the airport. I highly recommend it. Okay. Okay. Next question. Has a car ever gone supersonic? And the answer to that question is yes. Okay. Here is a supersonic car. They had a contest back in the 90s. A British company, Castrol, oil company, company that makes motor oil for your car, had a contest. They say we're gonna give $1 million to the first team that can go supersonic in one direction and then go supersonic in the other direction within 1 hour. Okay, so you couldn't just put a rocket engine on a car. You had to put basically a jet engine. Okay, it had to be something that you could refuel. All right, and they achieved this on October 15th. A team of British engineers achieved this on October 15th, 1997. Here's a video of it. Oops. Oh, I thought I might get.
Writing's not that easy.
Sorry
but
about that.
Grammarly can help. This sentence is grammatically correct.
Sorry about that. Had to get past it. Yeah. Okay. Now, this is a little plain. This is they're having fun. The speed record before was 391 miles an hour by the Americans. The British blew that away, and they actually did this on the salt flats in Nevada, in Black Rock Desert. Okay, so it was because they needed something really big, really large area, really flat with nothing in the way. So the salt flats or the desert in Nevada was a good spot for that.
SSC, you are clear to roll.
All right. So the first supersonic car. Okay. And I used to, and I couldn't find it again. They used to have a video where they actually had a cockpit cam and you could see the condensation around the cockpit window as you broke it. Okay. Yeah. Maybe you can find it on YouTube. I haven't looked for it lately. Maybe you can find that video yourself, okay, of it breaking the sound barrier. All right. Okay. Now, I used to have a bullwhip. You know, one of those bullwhips where you go whack. You know, with the whip and then snap. Okay. If you do it just right, then you practice it. And I have done it with the whip that wasn't mine. I had to leave behind. So whack. The tip of the tip of the whip can go supersonic, and that's where if you get a really sharp crack coming from a bullwhip, it's the sound. The very tip of that whip is actually breaking the sound barrier and creating a mini shockwave. Okay, bullets given a large enough bullet can also do that. Okay, so you can break the sound barrier yourself. Just get a really good whip. It'll take a little practice, but if you can get a really sharp snap, then the tip of that whip is actually breaking the sound barrier. Okay? All right. Yeah. All right. So, all right. I should go online and I should buy a whip. Just for this. Nothing else, just for this, because it's fun to do. All right. All right, next. Sound travels more quickly in liquids and solids. Okay? Sound travels more quickly in liquids and solids for a very simple reason. Can anybody think of it? Can anybody think of it? Sound travels more quickly in liquids and solids. Why? Yeah, density, because the particles are closer together. Okay. That's very simple reason. Okay. And it also travels with less energy loss. So it can travel, with greater distances before dissipating. Check this out. Whale song. Whale song. Wouldn't it be cool to know what they're saying? I think that whale is trying to talk to us. You know, wouldn't it be cool to have a whale English dictionary? Okay, wouldn't that be cool? Now they say that whales are as intelligent as we are. Okay? We have the same intellectual level, but we have two things on them that they don't. One, opposable thumbs, and two, we live on the surface, so we can control fire. You know, other than that, we don't know. We can't talk to them. Wouldn't it be super cool to know what they're saying? Play. It would just be ultra cool to know what they're saying. They've actually tried with porpoises, with dolphins. They've actually tried to communicate with dolphins. They haven't had a lot of success because dolphins, their lips, well, they don't have lips, so they can't make the "m" sound. They can make the "t" and the "p," but they can't make a "m." So they're having trouble. You know, the dolphins, they try, but we still don't have a whale or dolphin English dictionary, which is unfortunate. It would be really cool to know what they're saying. Yeah. Okay. Anyway, according to my research, the call of a humpback whale is louder than a Concorde jet and can be heard 500 miles away. Now, so if you went outside and you yelled at the top of your lungs, how far away could you be heard? How far do you think? How far away could you be heard if you went outside and it made as loud a sound as you could possibly make? Shouted at the top of your lungs, you know, quarter mile, half mile. I don't think 1 mile. Well, if a humpback whale shouted at the top of its lungs, and oh, by the way, they have lungs, they could be heard up to 500 miles away because the sound travels with very, very little energy loss. Okay. All right. Okay, so it's whale song. Really fun to think about. Okay, couple more notes to take and then we'll be done. All right, speed of sound in water, about 1,500 meters per second. About roughly 5 times faster than in the air because water is pretty dense. In rock, it's even faster, about 3,000 meters per second in earthquakes. All right. In a very elastic medium like steel, it's even faster, 5,000 meters per second. So if you want to hear if a train is coming, you put your ear down to the track. And if you put your ear to the track, you have one ear on the track and one ear in the air. Through which one are you going to hear the train coming first? Well, you're going to hear the clackety-clack through the steel because it travels faster and with less energy loss than through the air. Okay. All right. Okay. One more application of this, and this is historical. Let's say it's 700 years ago, and you're a Native American that live in South Dakota. Okay. You're part of a native part of the Sioux Indian tribe or Native American tribe that lived in South Dakota. It's September, winter is coming, and we need to find food to get us through the winter. So we're going to go hunt the bison. Bison are prevalent, but we got to go find them. We got to find the herd, right? Now, how are you going to find the herd? If you've never been to South Dakota, and I wouldn't be at all surprised if you have not, I have been to South Dakota, and South Dakota is just hills. Hills. Hill, go down, go up, go down, go up or down. They call them the Badlands. They're just hills. So how do you find the bison? Well, you go to the top of a hill and you look, but all you see is the top of another hill, right? So how do you find the bison, right? Well, instead of looking for them, you listen for them, because a bison is a huge animal. And when it's not necessarily just walking, but running on the ground, boom, 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 it's trampling the ground. If you get a whole herd of them running at the same time, it creates this tremendous vibrational wave in the ground, right? It's also very loud if you're standing next to them. But how far can it travel through the air? I don't know, a mile. And if a hill is in the way, most of the vibration goes up. So if you're standing on the ground, you're not going to hear it. So you don't listen through the air. Instead, you put your ear down to the ground and you listen through the ground. Okay? And you can hear the sound travel through the ground way, way farther away than you could travel through the air. So hunters would be out there, and there'd be one hunter on a hill over there with his ear to the ground. There'd be another hunter over there, with his ear to the ground. Said, "Hey, Jerry, do you hear him?" He says, "Yeah, I hear him. They're over there." He says, "I got him too. They're over there." And then you triangulate and you find the herd. Okay, kill 10 or 12 of them, and you have enough food to get your tribe through the winter. All right. And so by putting their ear to the ground, they could hear them. And that's actually a colloquial saying now, putting your ear to the ground. If you ever hear that in like the vernacular of English, they're putting their ear to the ground. What that means is they're assessing the situation. They're trying to figure out what's going on, right? And where does that phrase come from? It comes from the Native Americans putting their ear to the ground, trying to find the buffalo herd. And why that works is because sound travels so much better through solids than it does through gases. Okay? That's where that stuff comes from. All right. Okay. That's it for the day. Okay. The next topic of discussion is something called the Doppler effect, but we're not going to get into that now. I'm going to get into that next week. All right. Apologies. I took a little bit more time than I intended. What I'd like you to do, the homework for this, this section, is sound worksheet 1, and you can find. Get out of here. All right. Get out of here. And sound worksheet 1. Would you please open up a tab in Schoology? Let's see. Do I have wrong course? Physics. And if you go in this week's folder, okay, scroll down to the bottom and you'll find sound worksheet 1. Right? Sound worksheet 1. This is a series of questions, okay? All right, and I believe there's 10 of them. Yeah, there's 10 of them. I'd like please to complete this and submit it by the end of the day next Wednesday. We do not have class next Monday or Tuesday. You guys have the days off, okay? So you have ample time to take 20 minutes and fill out this sheet and then submit it to Schoology by the end of Wednesday, okay? All right. Sorry, I didn't give you a whole lot of time in breakout rooms to get started on this. There's 6 minutes left in class. I think what I'll do is I'm just going to let you go a little bit early today. All right. Why don't you take 6 minutes and get started on this thing? It can be on your own sheet of paper, or you can print this off. Makes no difference. Okay. Submit this to Schoology by the end of next Wednesday. Okay. All right. Any questions for me? This is a fun topic to talk about. All right. Hopefully you learned something that you didn't know before. I'm going to stop recording.